simple harmonic motion. For the simple harmonic motion, it's a special case of more general oscillation. Okay. And it's called a simple harmonic motion because it can be described by a harmonic function. Harmonic function is either sine or cosine function. So if we put x, p in a cosine function, so it will be written as this. Okay. And by taking derivative, we can see that the velocity function also takes a single harmonic function form. So it's negative omega xm omega t plus phi. Okay. So they can be described by the equation like this. And okay, so here some of the quantities appeared in the equation. What is xm? Okay, what we call it? Xm here. Amplitude. Okay. What do we call omega?
Frequency.
Is it frequency?
Angular.
Angular frequency. That's different. Angular frequency is different with the frequency, okay? And what do we call phi?
Initial
phase.
Okay, there are several names. The most common name is the initial phase. What is omega t plus phi?
phase.
That's a phase. Okay, phase is the argument in the sine or cosine function. This is the initial value for the phase if you put t equals to 0. Okay. And this is called the angular frequency. This is called the amplitude. You need to know what we mean by these quantities. Okay. Other quantities related will be period t. Okay. Frequency. This is the frequency. So omega is angular frequency, f is frequency. They are different things. And there are some relationship between them. In fact, okay, omega can be written as 2 pi over t or 2 pi multiplied by f. And here f equals to 1 over t. There is a relationship between the frequency. So these three quantities, angular frequency, frequency, and the period, they are related to each other. Okay, you need to know this relationship. These two, simple, okay, reciprocal. Omega equals to 2 pi over t, or 2 pi multiplied by f. So, frequency, if you know the frequency, to find the angular frequency, you only need to multiply it by 2 pi. Okay. So, in fact, that one we by angular. So, you change the frequency to the angular measurement. Okay. So, these are the quantities you need to know about the simple harmonic motion. So some of them can be directly get from the equation like this quantity. But these quantities, you have to do the calculation. But you can see, once you know the frequency, okay, you can also calculate the period and once you know the angular frequency, omega. So from here, you can also get period and frequency. Okay. So all these quantities you can either directly get it or do some simple calculation to find them out. Okay, from the equation if the equation is given. Now let's talk more about the simple harmonic motion. The simple harmonic motion, the most simple example is oscillation driven by the spring. Okay, so we know that for the spring, the force of the spring is given by the Hooke's law. Okay. F equals to negative kx. Okay, that's a force for a spring. Here k is the spring constant. And negative side means the force is opposite to the displacement. Okay, so if you have a spring, if you stretch it, the force is against your stretching. Right? So negative side. If you compress it, the force is against your compressing. It's always against your displacement. Okay. And this is for the spring system. In fact, any oscillation, you can write down the force in this form. A negative side, proportionality constant, and is proportional to the displacement. But for other systems, the constant here, okay, may not be the spring constant. So it always takes this form, but for the spring system, this k has a definite meaning, the spring constant of the spring. So it's a variable quantity. And once you know the constant here, okay, for us, it's just a spring constant. We will only consider the spring system, the oscillation by the spring system. So if you know this k, then you can calculate omega. Okay? The angular frequency equals to square root of k over m. So if you know k and mass, you can calculate omega. Or if you know omega, you can go back and calculate either k or mass. Okay. So here, if you look at these things together, one comment is that omega plays a very important role in all the quantities because it's related to many other quantities, right? So it's related to period, it's related to frequency, it's related to the mass and the spring constant. Okay, so omega is very important. Usually, if you try to find some unknown quantity and if you cannot find it directly, you need to think about omega. Maybe omega is a bridge to connect the unknown quantity and the known quantity. Okay? Like here, if you know omega from the equation and you know the mass, then you can calculate the k. Okay. As an example, we know t, the relationship between omega and t. Okay, so omega equals to 2 pi over t. On the other hand, omega equals to square root of k over m. So by solving this equation, it will give you a relationship between t and k. Okay. So for the spring system, here t equals to 2 pi over multiplied by square root of m over k. But usually we don't memorize this kind of equation, okay? Because that's a combination of this one and this one. But why need you know these equations are very fundamental? Okay, relationship between omega t, omega f, omega k f. Okay. So that's the fourth law. Another aspect we need to know about the simple harmonic motion is energy. Okay. The simple harmonic motion, for the simple harmonic motion, it's a spring system. So it has both the spring potential energy and the kinetic energy. Okay? And we know how to calculate the spring potential energy. U equals to 1/2 kx squared.